Okay, I just want to go through some of the problems, just a few quick example problems on reactions. So we had these problems last week that we worked in class, and there were some questions about this. So I just want to work through some of these real quickly, just to give you a sense of how to solve them and show you my thought process when I'm solving them. So this is problem 5a from the homework last week, where we looked at this reaction right here. We have 2SO2 plus O2 going to 2SO3. And we are given how much oxygen we have at 100 moles, and we're told the fractional excess of the other species is 0.2. In this case, SO2 is our other species, so it's in fractional excess at 0.2. And we're asked to find out how much we have of the reactants in the feed. So the good thing about this problem is we don't need to worry anything about the products, because that has nothing to do with the fractional excess and what's in the feed. In this case, we're just solving for how much O2 and how much SO2 we have, because those are the two reactants here. Well, already we should be able to just write out NO2 is equal to 100 moles. That's given in the problem statement. Put it there, put it in a box. The next thing we need to do is figure out how much SO2 we have. And in this case, we are told the fractional excess is 0.2, so let's write out the equation for fractional excess. And that is equal to the amount in the feed or inlet minus the amount stoichiometric over the amount stoichiometric. So that's the definition of fractional excess. So we need to find out, what we're trying to find out here is what this feed is, or how much is in the inlet or the feed stream to the reactor. We know the fractional excess, 0.2. So we need to find stoichiometric in order to find the amount of feed here. And this is where we need to pay attention a little to what's going on here. First thing we need to know is note what's in limiting and what's in excess. Well, we're told in the problem that SO2 is in excess. So if SO2 here is in excess, then that must mean O2 is limiting. So O2 limiting, SO2 excess. O2 limiting, SO2 excess. Now what we do is we find out how much the stoichiometric is based on the limiting reactant. So the amount stoichiometric assumes that all of the amount is equal to how much would be equivalent to the one that's in limiting. So if the limiting reactant is O2, the stoichiometric amount of SO2 would be the equivalent based on the stoichiometric ratio. So let's just write that out. It's a lot of words to talk about, but I think it's easier to show it out. The stoichiometric of SO2 is equal to 100 moles O2 divided by 1 mole O2, 2 mole SO2. And that's equal to 200 moles SO2. So let's just step through this step by step. Where did I get these? Well, 100 moles is how much I have of the limiting reactant, so given in the problem statement. So we take the limiting reactant and we simply multiply it by the stoichiometric ratio, 2 to 1. And that's 2 to 1 here from the balanced reaction equation. And that, just multiply that out here, that tells us that the stoichiometric amount of SO2 is 200 moles. That's how much SO2 we need to completely react away all of the O2, 200 moles. So that's how we get it. Now we're almost done here, so we can just go ahead and take this reaction, or this equation right here, and rearrange it to solve for the feed. So if I do that, number of feed, that's going to be the fractional excess multiplied by stoichiometric plus n stoichiometric. And we have everything we need here. Fractional excess was given as 0.2. And stoichiometric, we just found that, 200. Let me put a box on that just to clarification. And then n stoichiometric, 200. So if I take all those numbers in, then I will get over here number of feed of SO2, 0.2 times 200 moles plus 200 moles, and that's going to be 240 moles. And that's the answer. So the number of SO2 coming into our system, 240 moles, 100 moles of O2, and that was given in the problem statement. And that's pretty much how we work problem 5. And we can go down the line for all of the other parts, parts B, C, D, or etc., to do the same thing. First find out how much, what is limiting and what's in excess. And in this case, it turns out that O2 is the limiting in all the cases there, and the other species of the reaction is in excess. But once we go ahead and do that, know that, we can go ahead again and calculate the stoichiometric amount of the excess reactant, and then use the excess equation right here to go ahead and find out how much is coming in the feed or the inlet side of the reactor to come up with what we came here. Okay. Going to go through problem 6 here, which was again on the homework from last week, where we were given some information and we have to derive some other information. In this case, we are given some information about the initial number of moles for different reactants, and we're asked to find out what's leaving the reactor, or the outlet to the reactor, the final number of moles for all the different species. And we're told a fractional conversion, implying that not all of the reactants are going to react, and that in the end we're going to be left with some unreactive reactants left exiting our reactor, and then we're also going to be producing some product. So as is the case with all of these problems, we need to know what the limiting reactant is. If we don't know what the limiting reactant is, then we can't go about solving the problem. But limiting reactant, so we can do this in various ways, but let me just take 250 moles SO2 divided by 100 moles O2, and those are just given in here, given here in the problem statement, or given in the problem how many we have going into our reactor, and that's equal to 2.5 moles SO2 per mole O2, and that is greater than the stoichiometric ratio, which is 2 moles SO2 per mole O2. So this number right here, again, greater than the stoichiometric ratio, which was derived from the reaction equation. So what this implies is that the species on top, since it's greater than that, is this is the one is in excess, or SO2 excess O2 limiting, which is very good information to know. So the fractional conversion, and we're told that this fractional conversion here, we were told that the fractional conversion right here was for the limiting reactant. So this is the fractional conversion of O2, because that's the one that's limiting. And that's great. So we can write this out as fractional conversion is equal to moles reacted over moles fed. And we know everything in this equation except the number of moles reacted. So I can go ahead and write moles O2 reacted is equal to 0.5 times 100 moles. And I just got this. This was given in the problem statement. This was this right here, problem statement, FC, or fractional conversion. 100 moles is how much is fed into the reactor. So I just rearrange this right here to solve for the moles reacted. And that's going to give us 50 moles of O2. That's how much is reacted in this reactor. So we can go ahead and take this information to solve for the number of moles leaving the system. So the number of moles O2 out of the reactor is just simply the number of moles of O2 in minus moles reacted. And that's equal to 100 minus 50 equals 50 moles O2. And that's how much is coming out of the reactor. Again, we had 100 moles coming in. That was given in the problem statement. And 50 of those moles react. We just derived that right here. So if we start out with 100 and 50 of them react, we're left with 50 left. And that's how we came up with this. So the O2 leaving the reactor is 50 moles. So next I'm going to examine SO2 to find out how much is leaving our reactor, and that's equal to the number of moles of SO2 coming into the reactor minus the amount that react in the reaction. And we can find that from this information here based on how much O2 reacts. So that's just simply 250 moles, and that's given here in the problem statement. We're told 250. And how much moles of SO2 react? Well, that's minus 50 moles O2, and it's 1 mole O2 over 1 mole, 2 moles SO2, and that is just the stoichiometric ratio here, 2 to 1, 2 to 1. And so I can plug this in here to find out that 100 moles, this quantity right here is 100 moles of SO2 react. We started with 250, and if 100 react, then that means we're left with 150 moles SO2 coming out of our reactor. And there we have that. And so now we know how much O2 and SO2 is leaving the reactor. Just one little last part. We need to find out how much SO3 is leaving our reactor. So we can write out the number of moles of SO3 out. It's equal to the number of moles of SO3 in plus moles produced. In this case, SO3 is a product, so we're actually producing moles. We're creating the moles of SO3 rather than reacting them away. So we just have our equation here. Well, this is straightforward on this part. This is 0. We're not starting with any SO3 into our reactor feed. We're simply producing moles of SO3 according to this reaction. And we can use a similar setup to what we did to solve for these two here. That is equal to 50 moles of O2, 1 mole O2, 2 moles SO3, which tells us that we're producing 100 moles SO3. So again, I just use the number of moles of O2. So if we have 50 moles of O2 react, that produces in a 2 to 1 ratio according to the reaction equation, that produces a total of 100 moles of SO3. And since again no inlet, it's just the amount of moles produced is how much is coming out, 100 moles SO3. And that's how we go about solving these type of problems. We have to figure out, again, to give you an overview, figure out which is in excess, which is limiting. O2 is limiting, the other SO2 was in excess. Use that information of the fractional conversion of the limiting reactant to find out how many moles of the limiting reactant, in this case O2, react. So we react away 50 moles of O2, and then use that information to find out how much SO2 are reacting and how much SO3 are being produced, and simply take the difference between the outlet and the inlet based on what's being produced or reacted to find out these different quantities. And we do the same thing with B, C, D, etc. on the rest of problem 6. But that's how we go about solving it.